that we had in the last hour, it is for two things. It is because we have to understand that when number one, it is not practicable to count every single item of the population of interest a lot of times. So we take a sample, and there's been some very interesting mathematical work that's been done to tell us that a sample can be useful. Don't give up just because you can't count every single number. But we also need to understand that it's not free lunch. It's not free lunch. When you do a sample, there are certain things that you have to know. So when we say a sample is representative, that the estimates we get from a sample represent what we would have gotten from the whole population, you need to understand that it doesn't mean that the sample is the same population. I mean, that's common sense. That's common sense. If you have 100 people, like we have all of us in this class now, if we say that let's just take some samples on 10 people from the class and then compute their average age, or compute what is the most common profession, or compute, it's not going to be exactly the same thing as the whole population. But how do we now think about that in such a way that we are able to answer the questions? We're able to come to reach the conclusions that we need to reach to be able to solve the problem. For instance, like the kind of problem that our founder had the other time. And that means that we need to understand the ways in which the sample, what we get from the sample, is different from the population. And now we know that the relationship between the sample and the population is that if we took multiple samples and we estimated the mean from those multiple samples, the average of those means has been shown to kind of approximate the population sample. In fact, it does not become exactly population sample. The larger the size of each sample you take, the likelihood, the higher the likelihood that it would become exactly what you would have gotten if you get the population sample. Now, here's the problem. A funder would ask you, or somebody who's trying to answer the question would ask you, so now that you have a sample from your population, to what extent can I rely on this sample to make my decision? And here, like now, we talked about standard error. That if you calculate, people will be able to figure out that if you calculate the standard error from your sample, there are constants that you can multiply the standard error with that can give you certain bounds. And these are the things. So, for instance, if we took a sample of 1,000 people from Kenya, and then we looked at the estimate, only about 21% of the babies had sepsis. What mathematicians will be able to figure out is that if you look at the standard error in your sample and you multiply it by 1.96, your estimate from your sample plus or minus that 1.96 is what you would get if you keep on sampling 100. If you do this sample 100 times, and you understand why we want to do this sample 100 times, because if you sample them repeatedly, it is the average of all those samples that approximate the population mean. Remember, it is not the average of this your own sample. The thought experiment is that if you sample this your sample, different people sample multiple times, it is the average of those samples that approximates the population mean we actually want. But we don't know the population mean. We also do not want to do the work of resampling and resampling and resampling. So one thing we can do that we also know is that if we take this our single sample, we calculate the standard error. If we multiply the standard error by 1.96, for instance, the estimate from our sample plus or minus, that interval, we know that at this sample, we know that if we are taking our sample repeatedly about 100 times, the averages we would have gotten from those 100 times, 95% of the time would be within this range. I know it's a little bit complicated, but we need to understand that concept very carefully. Because what somebody will tell you is that, how do I know that? So for instance, you took a sample and then you found 21% of the people in the sample having sepsis. And then you found that 18% had hemorrhage. Your founder would ask, How do I know that if we are taking a different sample and different people are falling into the sample, the number would not have been reversed? Meaning hemorrhage would not have been 21% and sepsis be 18%. Because I don't want to make a mistake. How do I know? Because you took a sample, you didn't go and measure everything. The answer to that is that, well, you know, if I taking this sample multiple times, like 100 times, and I found the average of all those my samples, the average has been shown mathematically to approximate the population sample. But how do we know even that average since we didn't sample 10 times, 100 times? Well, we don't know the average. But one thing we know is that if we calculate the standard error in our sample, multiply it by a constant, let's use 1.96. If we multiply it by 1.96, if I add or subtract 1.96 from what I get from this my sample, I know that even if I had continued sampling 100 times, all the means and averages I would have gotten, at least 95 of them would have fallen within this range. So it is safe for us to believe that the population parameter, the population average itself would be within this range. Does that make sense? Now, so that is why you hear people talking about, so the convention most of the time is that, you see, if we are up to 95% sure, that's good enough. For most funders, for most people, 95%, if we know that there's 95% confidence, meaning that if we have sampled and sampled and sampled up to 100 times, I think 95% of the time, the value would have fallen within here. Meaning that the chance that the population parameter is within here is like 35 out of 100, then that's a good thing. Then we are confident enough. So if you tell your funder, for instance, that, okay, you know, the estimate for sepsis is 21. But when we do our confidence interval, meaning when we calculate our standard error multiplied by 1.96, what we get is 1.5. So if our estimate is 21, we know that it is 95% out of 100 times, the population estimate would have been either, say our average is 20, would have been either 21.5 or 18.5. What I just did is to remove, when I calculate the standard error by 1.96, I got 1.5. I removed that 1.5 I removed it from the average I got in the in this sample, which is 20%. That's the average estimate I got from this sample. If I remove 1.5 from it, it will be 18.5. If I add 1.5 to it, it will be 21.5. So I can tell them that the chance that the population parameter, that if we have counted everybody, that, you know, if we have counted everybody, there's 95% chance that what we would have gotten would be between 18.5 and 21.5. If we do the same thing for hemorrhage, and we see that the value would have been between 5 and 7, we know, okay, if the value for hemorrhage will be between 5 and 7, we are confident that the population parameter for hemorrhage is almost 5 and 7. But confident that the average for for sepsis is between 18.5 and 21.5, then we can say that under, even though we have used the sample, we have 95% confidence that the average for sepsis is much higher than the average for hemorrhage. So that is the train of thought that leads us to being able to make that confidence assertion that, well, Mr. Founder, you can go fund sepsis. There is up to 95% confidence just by measuring a single sample. That's why measuring a sample is helpful, saves money, saves cost, but it's not a free lunch. You have to be able to follow the thought process and do the appropriate estimates, not just the point estimate of how much of sepsis to find your sample, but also the standard error, but also the confidence bounds, the range of values, and show that the range of values are different from the comparison. Now, that brings us to what we call statistical tests.
I'm sorry to interject, sir. Your slide has not moved.
Yeah, because I have not moved. I have not moved either.
Okay.
So, what I've done is to ensure that conceptually we understand what we're doing.
Excuse me, sir.
Yeah.
Please, for clarity,
Yes.
I'm getting a little bit confused here.
Confused.
So does it mean that for the standard error,
Mhm.
is it that we are looking at the sample or the observations that we have? I mean, we were able to gather from the sample that we studied.
Yes. So when you take your sample, in your sample you would calculate a, a point estimate, right? Which is the estimate in your sample. Meaning, say we get 1,000 kids from Kenya now. Our point estimate, out of those 1,000 kids, we found 200 of them have sepsis. Our point estimate is what? 20%. Our point
Okay,
estimate, wait,
so
our point,
that means that we are calculating we are using it for the observations that we were able to generate from the sample.
yes.
Thank you.
Because we don't have any other thing, right?
Sorry if I may, Dr. Mona, I think the question is asking gets at the distinction between the sample and the population. I don't know if you could clarify those terms quickly.
No, that wasn't my question. I was trying to find out that for the standard error, is it applicable to the sample or the observations that we were able to extrapolate from the study, in the
Okay.
sample?
Well, I
Yes.
think we need to clarify, terminologies a bit. So when we talk about population, we are talking about everybody that's of interest, right?
Yes.
The target population. We are talking about all the kids in Kenya that we can never enumerate. All the neonates in Kenya that we can never enumerate, right?
Yes.
We understand that. Now, when we talk about sample, we're talking about the kids that we were able to select
Yes.
through our random process, right? Remember that what we really want to know is about all those kids, including the ones we have been able to include on our sample and the ones we cannot reach, right?
Yes.
Those are the people we are interested in. But we want to be able to talk about all of them without measuring all of them. We have information about only the kids we have in our sample now,
Yes.
right? So we will get a point estimate from our sample,
Yes.
right? We will get a standard deviation from our sample, get a standard error from our sample.
Okay. So basically the standard error is looking at the sample, the sample size that we have used, and not necessarily the observations we get from the sample.
Dr. B, do you understand? Dr. B, do you understand this question?
So I think it still gets back to the question of the terminology. So when we say sample in research, right, it's
Yeah.
not it's not everybody. It is basically when we say sample, we really mean your study population, right? It's different from the population, which is everybody that you could be interested in. And that's why it keeps giving the example of Kenya. You cannot study all the children in Kenya, but you can conduct a study of 1,000 kids. And those 1,000 kids in your study is your population, right? So if you talk about the observations that you can measure, that's the 1,000 people, and that is your sample. That's different from the full potential population of all the kids in Kenya that you will never be able to reach because there's millions and millions of them. And I hope that I've answered your question. So the standard error applies to your sample, which is the study population,
All
and
right.
not the full population. Exactly. Yeah.
I get it.
Yeah.
Okay.
Thank you.
Well, thank you for that clarification. So basically, now, the basic question we are trying to answer is: if you have a sample, how do we know that the conclusions you are reaching from your sample is not just as a result of random chance, meaning just as a result of the draw of the luck? If we had redone, we have taken another sample another day, it would have given us something else. And that is where statistical tests come into question. Because what they try to help us to do is to try to help us estimate what is the likelihood that had we enumerated everybody, the samples we would have gotten, what is the likelihood that within this range of values, what is the chance that that population parameter would have existed within this range of values? And that's why I was talking about all the central limit theorem, talking about all these distinctions, so that at the end of the day, we would know what exactly are these statistical tests telling us and why are they important. Because if you get a number of 18, you get a number of 20, well, if we had take different samples, would the numbers have, if we had take different samples, would the estimate of sepsis and pneumonia that reserved are reversed? It's possible, we do not know. It depends on, number one, what is the confidence interval, and how much of confidence, what is our extent of confidence in that interval. And this test help us to quantify. That is what these tests help us to quantify. Now, so a large part of what statisticians do is to develop this kind of test. Say, okay, if I want to answer this kind of question for someone or for a funder, and this is the kind of sample I'm able to take, how can I move from my sample to giving conclusions about what would have happened in the population at large, rather than my sample alone? And taking into consideration the role of chance in the selection of the observations that constitute my sample. So now, already we've talked about the central limit theorem. We spent a lot of time on it. It's a central principle in statistical analysis, and that's why we spend so much time on it. Now, look at this example. Dr. Koso Dr. Samuel from Koso Town basically wants to answer a very simple question. The MD of the hospital in their town has said that we need to know whether people consume more calories during Eid celebrations than regular days, right? Because if we know if people consume more calories during Eid celebration than regular days, maybe we should prepare that we will be getting, maybe there are more people, more diabetics that might get into emergencies around those days. Maybe we should prepare for more of those. But we need to test that assumption. We need to test that hypothesis. So what can he do? Well, at least we have nutritionists in the community who have been calculating the average number of calories that citizens consume on a regular day. And we know that it's 2,100. But this is the average that people consume over regular days. They don't know whether this is different from what people consume during Eid or not. So we can say, okay, what we would do is that on the day of Eid, we would compute how much of calories that people take and compare it to what is the average value for this community. So you get a sample of 100 people, you calculate how much of calories they take on each day. Remember, what else do you need to calculate? Because you're basically not measuring calories for every single person in the community on each day. Remember that. What did you do? You sampled just 100 people. Now, you have calculated how much of calories they take. The amount of calories those 100 people take, the average amount of calories you calculated, what would we call that? I mentioned it before. Somebody should tell me.
Say again.
So the sample is this 100 people, right? So the average amount of calories that they consume that we estimate would be what?
Would be the mean.
So that the mean of the for those people, what would we call it? It is what we call the point estimate, right? Say, okay, we get this 100 people. The mean calorie consumption for this 100 people is 1,600 calories on each day. That is the point estimate. For us to know how this point estimates relates to the whole population, what else do we need to calculate from this data?
The standard error.
We need to be able to calculate the standard error, because with the standard error, now we can put together a range that we can say that, oh, we know with confidence, with 95% of confidence. Of course, 95% is the convention, but we can calculate it for any amount of confidence. But we know with 95% confidence that had we measured everybody on each day, the amount of calories they've taken would have fallen within this range. Do you understand? For you to be able to compute that range, you need to calculate the standard error. Right? Once you calculate the standard error, what do? You multiply it for 95% confidence about we use 1.96. You multiply it by 1.96 and you add and subtract it from the point estimate. That is what gives you the confidence interval for what? For the calorie consumption on each day for this population. I want us to get this very clear. You know, if it's not clear, this is the fundamental basis of all statistical testing. So let's get it clear. If you don't get it clear, let me know. So, what is the question Dr. Koso wants to answer? The medical director is saying that, you know, we need to know whether people in this community does what? They consume more calories on each day. You know, we've heard many people say, oh, on each day I eat so much. We've heard so many people who say, you know, people just talk about eating so much. It's not like you're able to eat because, you know, there's so many other things you have to do. Okay, what do we need to do? We need to go collect data. But now, the ideal data would be to say, okay, let's get data from all the people in the community. And then, if it is more than 2,100, which is the standard that we know that people consume in this community, then we know that people consume more. If it is less than 2,100, we know people consume less. The problem, though, is that you cannot go and enumerate everybody on each day, within 24 hours on each day. So you're like, okay, what's the manageable number? 100. And we get 100 people. The problem is you have to always understand that even though we say 100 people, we sample this 100 people in a way that is representative, the estimate we get from the 100 people is not necessarily identical with the estimate we would have gotten had we sampled everybody in the population. So we have to resolve the role of chance. If we had by chance sampled another 100 people, even though they're also representative, they would have given us another number. So we have to find a way to answer the guy who would say, this 2150 you got, had you done the sample a second time, you would have gotten 1950 instead of 2150. And therefore, you don't even know. I mean, the conclusion you are reaching is really just driven by your sample, by chance, the luck of the kind of people that ended up in your sample. So you have to be able to account for that luck. And that is why we are doing these things we are doing now. That is why the point estimate is not sufficient, because we know that there's some chance embedded in that point estimate. To disentangle that chance is why we do the next things we do, which is statistical testing. And what do we do?
Sorry, sir. Sorry, sir. I have a question.
Yes.
If you go to the slide before this one, the 21,000 calories that was gotten from the nutritionist on a regular day.
Yes.
I'm a little confused. Is this still from these 100 people that we are sampling?
No. So look at, think about the community now. Say we are in a community here. You know, we have a nutritionist who's been living in this community for 20 years. Over 20 years, everybody in this community have been coming to this nutritionist every day, over time, asking all sorts of advice. This nutritionist has been measuring everybody over time. So we have an average. We have what we call a standard. A standard. This nutritionist has been involved in many experiments that have said that 2,100 is the best amount of calories that, you know, adults should be taking on the average. So that's like a standard that we know, either an empirical standard what many people are saying, or that we know from research that when people take 2,100, of course, I'm not taking that. I'm not saying that's a fact. I'm just saying for the purpose of this thought experiment, 2,100 is what experiments have shown that if people take this amount, they would be good. They wouldn't get complications. So the question we are trying to answer is, well, on each day, do people go beyond this 2,100 that is ideal? So 2,100 is an ideal, it's an ideal, one way or the other, whether an empirical ideal or a scientific ideal or some kind of other kinds of ideal. And it might just be 2,100 calories. You know, we have famine in the community right now. The district authority has said that nobody should be taking more than 2,100 calories per day. Or the nutritionist that. So just think, you leave the nutrition experts apart. It could be a figure that nutrition expert decides that is the best figure. It could be a scientific consensus. It could be an economic consensus. But what we really want to figure out is that are people taking amount of calories that is different from 2,100? Because 2,100 is the ideal that serves our purpose. Does that make sense?
Yes, it does.
So essentially, what we're trying to do is to test whether our population, the parameter in our population is different from a set ideal. And how do we answer that question? Is that we go to our population, we take a sample. When we get a sample, we get the point estimate from the sample. But then the question becomes, well, you didn't measure everybody in the community, you measure the point estimate. How do you convince me that your point estimate is not just a product of chance? Meaning that it's not just a product of the people who fell into your sample when you did your sample. Maybe if you had redone your sample, you would have gotten another estimate. Now you got 2,150 when you got your 100, your 100 people. How do we not know that if you had done next, if you had done the next one, you would not have gotten 2,050? So that is the real question that as a statistician you have to be able to think through. That is it really truly different? And that is what people mean when they say it is statistically significant. Is it truly different, or is it a question of chance? How do we know that? Is that we also look at the standard error and we compute the confidence bounds. When we compute the confidence bounds, if, for instance, we calculate the point estimate in our population to be what? To be 2,500, right? And we compute this confidence bounds. The standard, our standard, we compute the confidence bounds, and it turns out that our confidence bounds is 300, right? What it means is that had we measured our whole population with 95% confidence, we can say that if we had measured our whole population, the average would be somewhere between 2,200 and what? Somebody should tell me.
2,800.
And 2,800. It's somewhere between 2,200 and 2,800. Now, if that is what we got, what would be your conclusion to the district's management? Are people eating more on Eid or not? The standard is 2,100.
It will mean that they are eating more.
It will mean that they are eating more. So you can tell with 95% confidence that had we done this 100 times, 95% of the times, we would have come to the conclusion that people are eating more. But there are two things you need to do. And what we have just done right now is what is called the one sample t-test. Remember the features here. The one sample t-test started with what? A hypothesis. This hypothesis was two-sided. I will explain what each of those means. It comes with what is the hypothesis in this our case. I've explained the problem to you. Now you would have to couch this problem in scientific terms for me. What is the hypothesis in this problem we just solved? Somebody should tell me the hypothesis here. Well,
that the mean calorie consumed on the eat day is not equal to the mean calorie consumed on the regular day.
so that's partly a trick question, to be honest, because what you would ask me is, are you asking about the null hypothesis or the alternative hypothesis?
And they appear to be the same.
I didn't hear that.
They appear to be the same here. Maybe just a minor error.
Okay, just a moment. Whenever we're talking about statistical testing as a procedure, we need to have we need to have two types of hypotheses. We need to have the null hypothesis and the alternative hypothesis. Right? So usually the conventional way people would try to say it is that the alternative hypothesis is what we are trying to prove. That's not, I mean, in rigorous terms, that's not exactly what we're saying. But for the purpose of this conversation, let's say that the alternative hypothesis is what we're trying to prove. Which in this case is what? What are we trying to prove? As researchers, what are we trying to prove to the nutritionists and the district authorities in this our little study that we just did?
That on each day celebrations, the members of the population consume calories of more than 2,100.
Okay. Basically, I mean that's one formulation, which is good. That on each day,
We are saying that they consume less.
I mean, on each day, we are saying that on each day, members of the population consume calories differently than on days that are not each day. What I said now is just a little bit different from what you have said. What you have said is correct also. It's correct also. All these formulations are correct. You can say, well, the alternative hypothesis is that on each day, people consume differently than they consume on regular days. Somebody can say that on each day, people consume more than they consume on regular days. Somebody can say on each day, people consume less than they consume on regular days. In actual fact, from the experiment we did, all this could have been correct, but your alternative hypothesis should reflect the actual questions you want to answer. In this formulation, our nutritionists or the people in our committee are thinking that people eat more on each days, not that people eat less. If we are interested, if we had already concluded that it can only be more, and we are interested in testing on each days, do people eat more? Well, that's our alternative hypothesis. But that would be a one-sided hypothesis. That would be different than if I had said on each day, people eat more or less than on regular days. Or on each day, people eat differently, eat a different amount of calories than on regular days. Because that would mean that we are testing that it can be more, it can be less. Which would be what? A two-sided hypothesis. Does that make sense?
Yes.
But I don't want us to go into siding now. I don't want us to go into one side and two sides.
Yes.
I want us to just stick to null and alternative hypothesis for now. So alternative hypothesis is what we're trying to prove, to speak loosely. Now, the null hypothesis would be the opposite of it. So can somebody frame the null hypothesis for our current population for me? For our current study.
Mean calories consumed during each is not different. It's not different or is equal to mean calories consumed on regular days. But the sign here is
No. Yes. That's my error. I mean, that's my error. But at least now the error has taught me something that you actually know what you're talking about. You're not just reading from the slide. So the null hypothesis is that on each day, people do not eat differently than on regular days. Basically, on each day, what people eat is equal to what they eat on regular days. Is there anybody who so far is kind of lost in these terminologies and these concepts? Because it's important that you really understand these terminologies and concepts, because a lot of what you will do down the line will be based on these concepts. Now we understand our alternative hypothesis and our null hypothesis. One thing I want you guys to do for me is that before the next class, let everybody formulate at least one null and one one null hypothesis and one alternative hypothesis. Think about the study, formulate a null hypothesis and formulate an alternative hypothesis, and you can send it to the Stats Clinic email. Now we have our hypothesis, right? How do we move from our hypothesis to now knowing that we've ruled out the role of chance? That's what we talked about. What do? We take our point estimates, we calculate our standard deviation, we calculate our standard error, we multiply by the constant for 95% confidence. Since we have decided that 95%, we are fine with 95% confidence, we don't need to have 100% confidence. And then we estimate what is the upper boundary of the intake on each day, what is the lower boundary of the intake on each day, right? And then we answer the question. Is there anybody who did not get this? Now, somebody would ask, whenever I hear about statistical tests, yes, I hear about confidence intervals. I hear about point estimates. We know what point estimates are now. I hear about standard deviation. We know what standard deviation is now. I hear about standard error. We know what standard error is now. We know how point estimate, standard deviation, standard error are all related to our sample and our population. We also hear about confidence intervals. We hear about the upper limit of confidence interval, the lower limit of confidence interval. Now we know what each of those mean. We know how we compute them once we get to our standard error. And we know how we use them to come to a decision about whether our estimate can be due to chance or not. Somebody would ask, then what about, but I've not heard anybody talk about the all-powerful p-values. What are p-values? You see, basically from everything we've talked about now, we've essentially covered p-values. P-value okay, so basically now, if we have calculated basically if we do a one sample t test, when we calculate the test, what it does, let's keep all the calculations that I've shown. Say you estimate this in a computer. At the end of the day, what you estimate is a t-statistic. Now, scientists have developed tables that, based on the t-statistic you estimate, they can give you a particular p-value. I mean, usually in those days, we used to look at it in the tables. Now the computer will give you that figure. And based on the p-value, you can conclude whether you have a number that, you can conclude whether you have a number, whether you have the numbers you are getting are statistically significant, meaning that after factoring the role of chance into it, these numbers are still different from the 2,100 you got or not. So basically, what we have just described is what is a one sample t-test. Now, the other type of test that I want to talk about is similar to a t-test in the sense that what we are doing is comparing one average, one mean to another figure. But remember in the last time when we talked about that, we were comparing the mean to what? To a standard value. A standard value that might be a scientific consensus, might be an economic consensus, might be whatever. But here now, what we are comparing the mean to is another mean. So essentially, a t-test is a test that is used to compare a mean to another value. That value can be a standard value in the case of a one sample t-test. It can be two other means in the case of two sample t-test. Now, for two sample t-test, I will talk about only one type of two sample t-test now, which is called a paired sample t-test. Now, think about it. There are times when observations that we're interested in are really paired. Let me give you an example now. You see, somebody might be interested in knowing whether is the weight of a person related to their height. Is the weight of a person related to their height? You know, I mean, so the easiest way to go about this would be to do what? Say, okay, is the weight of students in Lagos related to the height of students in Lagos? Of course, we can't measure all the students in Lagos, so we take a sample of students, 100 students in Lagos. And what will we do? We measure their weight and we measure their what? Their height. One thing, though, that you need to bear in mind is that on each student, you're measuring the weight, and maybe that might be a little bit confusing of an example. Let me give you a different example. We can say we want to measure whether the amount of knowledge that students have about statistics before they undertake a test is related, is related to the amount of knowledge they have after the test. Meaning students who know a lot more before the test would know before the class. After the classes, they even know a lot more compared to people who knew a little before the class. After the class, they still know more, but they know a little. I mean, people who knew much more before then still know much more before then. The way to do that type of t-test is that we don't just calculate the amount of knowledge that everybody have all together. No. What we calculate in this population is what? The difference between the paired observations. On each individual, we have paired observations. The amount of knowledge before classes, the amount of knowledge after classes. You take the difference from each of them and then find the mean of that difference. Sometimes people fall into the error of just finding the mean of all the after-test scores and then just finding the mean of all the pre-test scores. I won't go into, it can be mathematically proven that such analysis can mislead, but we don't have the time to go into the details of that right now. But just know that when you have paired observations on each unit, the way to test your hypothesis is a paired sample t-test. And what it does basically is to find the difference on each unit first, and then find the average of those differences divided by its standard error. Just like what we did in the last one. But here, now we're talking about paired observations. So, for example, you are the new CMD at Lagos Hospital, and you ask all the resident doctors how many hours they worked last week, and you calculated the mean. You obtain 72 hours. Okay. So, 72 hours, it's crazy. Basically, people are not sleeping at all. They will make mistakes. They will commit medical errors. Okay. So, you have to do something about it. You hire other staff and shift some of the work from the doctors to those. Now, after 12 weeks, you ask everyone how many hours they worked in the last week. And now you obtain this table. At week 0, before you hired your staff, this is what each person works. At week 12, this is what each person works. You really want to know if your hiring practices change the number of hours resident doctors work. So what you do is you conduct a PhD test and test the null hypothesis. Can somebody tell me what the null hypothesis would be in this study? We're running out of time. Yeah.
H naught will be, there is no difference in the hours of in the number of hours worked by resident doctors at week 1 and 12.
And what will be the alternative hypothesis?
The alternative hypothesis will be that there's a difference. There's a difference in the average number of hours worked by resident doctors at week 0 and at week 12.
Is that a two-sided or a one-sided alternative hypothesis?
It's two-sided because it's saying a difference, so it could either be negative or lower.
So
or
if
higher.
you needed to frame a one-sided hypothesis here, what would be the most logical one-sided hypothesis for you here? Do you think, are we thinking that maybe people are even working more?
Reduced?
Yeah. So did it reduce?
It will be that it's
So
reduced by week 12.
Yeah. So one-sided hypothesis might be that the amount of hours, I mean, residents are working is reduced after the hiring process. So when you look at the SPSS table here, well, you will see that this is the mean. They computed the mean, the average for week 0, average for week 2. They've done all the calculations about the difference in the PS. This is the standard deviation. They've calculated the standard error for the mean from the standard deviation. And what they are showing us here is that this is the mean difference, right? Between week 0 and week 12. This is the standard deviation, 3.792. This is standard error, 0.277. Now, when they add, they've done the 1.96 times, standard error that we talked about. When they add it to the point estimates, they get 7.31 for the lower limit. That's when they remove it. They get 8.41 from the upper limit, meaning that the actual difference in time between week 0 and week 12, the actual difference in amount of hours that we worked is 7 to 8. Does this mean that people are working more, they are working less, or there's no difference? Somebody should give me an answer. Are they working more?
There's
Working
no difference. There is a difference, but it's not significant.
Okay.
But I think they're working less.
I think it's significant.
Now, those are all
Oh, yeah,
those
they
are
are
all
working.
interesting answers that I would like each of us to defend, but looks like we are really running out of time. So the first
So,
question
sorry, sir. I think one thing is one thing we you would have helped us do is from that one sample test to understand the readings from those tables, right? So yeah, we have maybe even when you are talking about the p-value, I know there was a slide you presented where we saw some formulas and then they brought minus 8 point something as a value and how that works. Yeah.
Okay. No,
And then
let's
to
leave
help
the
us explain this.
let's leave the p-value by the side now. So look at this. When you look at this table down here, the lowest table on the slide right now. Look at the first words here. Pair 1, week 0 minus week 2, right? Do we see that? No, do you see that? Week 0 minus week 12, right? Do you
Yes.
see that?
Yes.
Because that is very important information. If they are treating week 12 minus week 0, the meaning of the values you get here would be very different. So here, what they are doing is they are removing the number of hours that are being worked at week 12 from the number of hours that are being worked at week 0, right? Meaning that if you get a positive number now, it means that there are more hours being worked during week 0, right? And if you get a negative number, it means there are more hours being worked during week 12. So how you arrange this does matter. So you have to always be looking at how did you arrange your data and what this output is exactly saying. So basically, when they have looked at the difference between each person, each of the 15 people, so basically what they did here is that they took 15 residents out of the residents they had here, right? Because they don't want to take all the residents in the world, all the residents in the hospital. Now they asked each resident, you have to tell us how many hours you were working. The residents told them. Okay, then they hired people. 12 weeks later, they came back to this resident. Tell us how much you are working also. And then they put the numbers here and they found the difference between, the difference of hours that each resident works. When they found the difference, all those differences that they found, now they found the mean of the differences. You know, if we were doing one sample t-test, what would we have found? We would just, because there's just one sample, there's just a set of observations, not 2 observations on each person. We will just find the average of that set of observations. For instance, if it were one sample, what this would have looked like is that, okay, we know that the average number of hours that people were working usually is 72 hours per week. Okay, in week 12, are people working as much as standard working hours? That would be a one sample t-test, because then what we'll just do is collect all the hours they are working in week 12, find the average of all those hours, find the standard error of those hours they were working in week 12, and compute the confidence interval for that. And then check whether the confidence intervals does not include 72 hours, which is the standard that has been predetermined. That would be a one sample t-test. But because here, what we have is serial measurement. It's 2 measurements, paired measurements on each individual. Now what we do is define the difference of each pair. The average of those it is the differences that will now constitute what we will work with. We find the average of those differences, the standard deviation in those differences, the standard error in those differences, and use the standard error to calculate the upper and lower bound of the difference. So if the difference is 0, we know there is no difference. If the difference is a positive number, we know that week 0 is higher than week 12. If the difference is a negative number, we know that week 0 is lesser than week 12. Does that make sense?
Yes, it does.
Yes, it does.
So that is
So
what we
how
see
does
here.
the confidence interval, how do we interpret the confidence interval in this regard? Since there is a confidence interval, I'm a little confused as to which
So
of
the
those
confidence
values.
interval. Yeah. So the confidence interval here is that, had we measured the time worked by all the residents in the hospital, the difference between hours worked in week 0 and week 12, we have 95% confidence that that difference is between 7.3 and 8.4. Meaning that, as we measured everybody, we think that the actual figure that we would have gotten is between these. How do we know? Because we have mathematical theory that told us that if we had resampled 15 people from all the residents we have multiple times, and we had recomputed this figure multiple times, 95% out of the 100 times that we resampled, the number we get for the difference would be between 8.4, would be between 7.3 and 8.4. And we know that that number, we know that that range, if it contains, 95%, it is very likely, it is, I mean, we are 95% confident that it contains the population parameter. Of course, nobody measures the population parameter. Does that make sense to you? So, in the short run, people would say that we are 95% confident that people worked less in week 12, or people worked more in week before hiring by up to 7.3 to 8. I mean, we are by between 7.3 to 8.4 hours. Right? If the range had included 0, say what we got here was minus 2.4 hours to plus 5.2 hours, you would have said we are not sure, because the population parameter could have been anything from minus 2.4 to 0 to plus 2.4 to plus 5.2. So we don't know where the population parameter actually falls in that range. But we are 95% confident that it falls somewhere in that range. But because the whole of that range excludes 0, we know that this confidence, we know that, yes, the hiring worked. People worked less after we hired new people. Now, I have told you manually how we compute it. Another way to have computed it is that if we had asked our computer, I will not go into the formula for a t-statistic. Yeah, we don't have the time now. But one thing we could have computed from these numbers is what we call a t-statistic. We could have computed it for that. If you get a t-statistic and you combine it with the difference of freedom, we have tables that where you can just look at your t-statistic and you look at the your DF and you can pick up the p-value that corresponds to it. But I tell you, the p-value only goes to confirm what we know from our confidence interval. I know this is a little bit confusing, but the more you talk about these concepts as the weeks go by, the more you would appreciate the role of chance and how statistical testing helps us to disentangle the role of chance, and how the central limit theory and what it shows us about the estimates in a sample and the relationship between estimate in a sample and the population parameter, how that helps us to be able to move from samples to making inferences about populations. So there's a second example here, but it really comes down to the same concept that we've really described. Here it's just blood pressure. We're looking at the blood pressure before and the blood pressure after we take a particular drug to know whether is the drug able to lower blood pressure. Now, what we do is that for each individual, we find the difference between when the blood pressure before and the blood pressure after. And then those differences, we will find the average to constitute our point estimate for the population we observed. We will estimate the standard error, estimate the bounds of the confidence interval. And if the confidence interval range excludes 0, we know that this difference is different from 0. Remember that the null hypothesis here is that the difference between blood pressure before and after this drug medication is 0. Just like the null hypothesis in our last experiment is that the difference in hours worked before and after the new hiring was done is 0, meaning there's no difference. And our alternative hypothesis is that the difference is not 0. So when we got 7.2 to 8.4, we know that the difference is not 0. It does not include 0. Now, here, when we got 7.4 to 8.3, we know that the difference is not 0. So now, the final one, I don't think we have much more time, but I think the final one here that we talk about is the okay, I don't think we can get to ANOVA today. The final one I will talk about is the independent samples t-test. The independent samples t-test is still the t-test. The only difference in these 3 different types of t-tests we are talking about is what are we comparing the mean to? Remember, t-test is a way of comparing the mean to something. When we are comparing to a standard value, that is what? a one sample t-test. When we are comparing it to another mean, but the observations are paired, and the real thing we are interested in is the difference in paired observations, then that's a paired sample t-test. The independent sample t-test is that the observations are on different units, different entities. And the example I will give you here is if we conduct a randomized trial. Say we are conducting a randomized trial of whether a particular drug works. Of course, we assign some people to the drug, some people to placebo. Now, say this is a drug for blood pressure. Okay. We measure the average in the people who took placebo. We measure the average in the people who took blood pressure. See, so when you take, the people who are in the placebo group, for this particular example we are making, are different from the people in the medication group. So we find the average of people in the placebo group, the average of people in the medication group, and we compare the averages. So what do? We compare the average of this one to this one. And how do we compare those averages? We basically remove the average of the placebo from the average of people who took the medication. And now the standard error that we would divide by is where the difference in the actual computation comes in. It is what we call the pooled standard error. Because that standard error, remember that the people who are in placebo, they would have their own standard error. The people who are in medication, they will have their own standard error, which is not necessarily the same. So the pooled standard error, which is essentially a standard error of the difference between them, is what we would use in this situation. I don't think we have a lot of time more. I would have loved to make a few more comments about the independent t-test, and we still have the ANOVA that we've not been able to do, but hopefully during the next class, we'll be able to get down to those. We spent a lot of time on really apprehending certain concepts. I think that, I spent more time on those things because I believe that at the end of the day, the key about statistics is not calculation. It's not computer. Today, there are computers that can do all the calculation, all the computation for anybody. But you have to understand what those numbers mean, what those concepts mean. When we talk about confidence interval, what does it mean? When we talk about point estimate, what does it mean? When we talk about standard error, what does it mean? When we say the target population, what does it mean? When we say the sampled population, what does it mean? Because if you do not understand those things, all the numbers that your computer spits out means nothing. You would just, you would just be wallowing in a lot of confusion. At this point, I want to bring the class to a close. Thank you very much.